You wrote a book about aliens. So the big question, how many alien civilizations are out there?
Yeah, that's the question, right? The amazing thing is that after 2.5 millennia of, people yelling at each other or setting each other on fire occasionally over the answer, we now actually have the capacity to answer that question. So in the next 10, 20, 30 years, we're going to have data relevant to the answer to that question. We're going to have hard data finally that will, one way or the other, even if we don't find anything immediately, we will have gone through a number of planets. We'll be able to start putting limits on how common life is. The one answer I can tell you, which was an important part of the problem, is how many planets are there? Right. And just like people have been arguing about the existence of life elsewhere for 2,500 years, people have been arguing about planets for the exact same amount of time. Right. You can see Aristotle yelling at Democritus about this. You can see they had very wildly different opinions about how common planets were going to be and how unique Earth was. And that question got answered. Right. Which is pretty remarkable that in a lifetime you can have a 2,500-year-old question. The answer is they're everywhere. There are planets everywhere. And it was possible that planets were really rare. We didn't really understand how planets formed. And so if you go back to, say, the turn of the 20th century, there was a theory that said planets formed when two stars passed by each other closely, and then material was gravitationally squeezed out, in which case those kinds of collisions are so rare that you would expect 1 in a trillion stars to have planets. Instead, every star in the night sky has planets.
So one of the things you've done is simulated the formation of stars. How difficult do you think it is to simulate the formation of planets, like simulate a solar system through the entire evolution of the solar system? This is kind of a numerical simulation sneaking up to the question of how many planets are there.
That actually we're able to do now. You can run simulations of the formation of planetary system. So if you run the simulation, really where you want to start is a cloud of gas, these giant interstellar clouds of gas that may have 1 million times the mass of the sun in them. And so you run a simulation of that. It's turbulent. The gas is roiling and tumbling. And every now and then you get a place where the gas is dense enough that gravity gets hold of it and it can pull it downward. So you'll start to form a protostar. And a protostar is basically the young star of this ball of gas where nuclear reactions are getting started. But it's also a disk. So as material falls inward, because everything's rotating, as it falls inward, it'll spin up and then it'll form a disk. Material will collect in what's called an accretion disk or a protoplanetary disk. And you can simulate all of that. Once you get into the disk itself and you want to do planets, things get a little bit more complicated because the physics gets more complicated. Now you got to start worrying about dust, because actually dust is the wrong word. It's smoke, really. These are the tiniest bits of solids. They will coagulate in the disk to form pebbles, right? And then the pebbles will collide to form rocks, and then the rocks will form boulders, et cetera, et cetera. That process is super complicated, but we've been able to simulate enough of it to begin to get a handle on how planets form, how you accrete enough material to get the first proto-planets or planetary embryos, as we call them. And then the next step is those things start slamming into each other to form, planetary-sized bodies. And then the planetary bodies slam into each other. Earth, the moon, came about because there was a Mars-sized body that slammed into the Earth and basically blew off all the material that then eventually formed the moon.
And all of them have different chemical compositions, different temperatures?
Yeah, so the temperature of the material in the disk depends on how far away you are from the star. So it decreases, right? And so there's a really interesting point. So close to the star, temperatures are really high. And the only thing that can condense, that can kind of freeze out, is going to be stuff like metals. So that's why you find Mercury is this giant ball of iron, basically. And then as you go further out, the gas gets cooler, and now you can start getting things like water to freeze, right? So there's something we call the snow line, which is somewhere in our solar system out around between Mars and Jupiter. And that's the reason why the giant planets in our solar system, Jupiter, Saturn, Uranus, and Neptune all have huge amounts of ice in them, or water and ice. Actually, Jupiter and Saturn don't have so much, but the moons do. The moons have so much water in them that there's oceans, right? That we've got a number of those moons have got more water on them than there's water on Earth.
Do you think it's possible to do that kind of simulation to have a stronger and stronger estimate of how likely an Earth-like planet is? Can we get the physics simulation done well enough to where we can start estimating, like, what are the possible Earth-like things that could be generated?
Yeah, I think we can. I think we're learning how to do that now. So, one part is like trying to just figure out how planets form themselves and doing the simulations like that cascade from dust grains up to planetary embryos. That's hard to simulate because it's both. You got to do both the gas and you got to do the dust and the dust colliding and all that physics. Once you get up to a planet-sized body, then you kind of have to switch over to almost like a different kind of simulation. There, often what you're doing is you're assuming the planet is this sort of spherical ball, and then you're doing like a 1D, a radial calculation. You're just asking like, all right, how is this thing what is the structure of it going to be? Like, am I going to have a solid iron core, or am I going to get a solid iron core with that liquid iron core out around it like we have on Earth? And then you get, a silicate, kind of a rocky mantle, and then a crust. All of those details, those are kind of beyond being able to do full 3D simulations from ab initio, from scratch. We're not there yet.
How important are those details, like the crust and the atmosphere, do you think?
Hugely important. So I'm part of a collaboration at the University of Rochester where we're using the giant laser. This is called the Laboratory for Laser Energetics. We got a huge grant from the NSF to use that laser to slam tiny pieces of silica to understand what the conditions are like at the center of the Earth, or even more importantly, the center of super Earths. Like this is what's wild. The most common kind of planet in the universe we don't have in our solar system, which is amazing, right? So we've been able to study enough or observe enough planets now to get a census. We kind of have an idea of who's average, who's weird. And our solar system's weird because the average planet has a mass somewhere between a few times the mass of the Earth to maybe, 10 times the mass of the Earth. And that's exactly where there are no planets in our solar system. So the smaller ones of those we call super Earths. The larger ones we call sub-Neptunes. And they're anybody's guess. Like, we don't really know what happens to material when you're squeezed to those pressures, which is like millions, tens of millions of times the pressure on the surface of the Earth. So those details really will matter of what's going on in there, because that will determine whether or not you have, say, for example, plate tectonics. We think plate tectonics may have been really important for life on Earth, for the evolution of complex life on Earth. So it turns out, and this is sort of the next generation where we're going with the understanding the evolution of planets and life. It turns out that you actually have to think hard about the planetary context for life. You can't just be like, oh, there's a warm pond, and then some interesting, chemistry happens in the warm pond. You actually have to think about the planet as a whole and what it's gone through in order to really understand whether a planet is a good place for life or not.
Why do you think plate tectonics might be useful for the formation of complex life?
There's a bunch of different things. One is that, the Earth went through a couple of phases of being a snowball planet. Like we went into a period of glaciation where pretty much the entire planet was under ice. The oceans were frozen. Early on in Earth's history, there was barely any land. We were actually a water world, with just a couple of Australia-sized cratons, they called them, protocontinents. So those, we went through these snowball Earth phases. And if it wasn't for the fact that we had kind of an active plate tectonics, which had a lot of volcanism on it, we could have been locked in that forever. Like, once you get into a snowball state, a planet can be trapped there forever, which is, maybe you already had life form, but then because it's so cold, you may never get anything more than just microbes. Right. So what plate tectonics does is because it fosters more volcanism, is that you're going to get carbon dioxide pumped into the atmosphere, which warms the planet up and gets you out of the snowball Earth phase. But there's even more really important things. I just finished a paper where we were looking at something called the hard steps model, which is this model that's been out there for a long time that purports to say, intelligent life in the universe will be really rare. And it made all these assumptions about the Earth's history, particularly that the history of life and the history of the planet are have nothing to do with each other. And it turns out, as I was doing the reading for this, that Earth probably early on had a more mild form of plate tectonics, and then somewhere about 1 billion years ago, it ramped up. And that ramping up changed everything on the planet, because here's a funny thing. The Earth used to be flat. What I mean by that, right? So all the flat earthers out there can get excited for 1 second.
Clip it.
What
Still
I mean by that is that there really weren't many mountain ranges, right? The beginning of, I think the term is orogenesis, mountain building, the true Himalayan-style giant mountains, didn't happen until this more robust form of plate tectonics, where the plates are really being driven around the planet. And that is when you get the crusts hitting each other and they start pushing into these Himalayan-style mountains. The weathering of that, the erosion of that, puts huge amounts of nutrients, things that microbes want to use, into the oceans, and then what we call the net primary productivity, the bottom of the food chain, how much sugars they're producing, how much photosynthesis they're doing, shot up by a factor of almost 1,000. Right, so the fact that you had plate tectonics supercharged evolution in some sense. We're not exactly sure how it happened, but it's clear that the amount of life, the amount of living activity that was happening really got a boost from the fact that suddenly there was this new vigorous form of plate tectonics.
So it's nice to have turmoil in terms of temperature, in terms of surface geometries, in terms of the chemistry of the planet, turmoil.
Yeah, that's actually really true, because what happens is if you look at the history of life, that's it's an excellent point you're bringing up. If you look at the history of life on Earth, we get, abiogenesis somewhere around at least 3.8 billion years ago. And that's the first microbes. They kind of take over enough that they really do, you get a biosphere. You get a biosphere that is actively changing the planet. But then you go through this period they call the boring billion, where it's 1 billion years and it's just microbes. Nothing's happening. It's just microbes. I mean, the microbes are doing amazing things. They're inventing fermentation. Thank you very much we appreciate that. But it's not until sort of you get probably these continents slamming into each other, you really get the beginning of continents forming and driving changes that evolution has to respond to, that on a planetary scale, this turmoil, this chaos is creating new niches as well as closing other ones. And evolution has to respond to that. And somewhere around there is when you get the Cambrian explosion, is when suddenly every body plan, evolution goes on an orgy, essentially. So yeah, it does look like that chaos or that turmoil was actually very helpful to evolution.